we have already seen the equation of progressive wave. In case of sound wave, particles of the medium do not vibrate perpendicular to the direction of propagation of the wave. Sound wave is not transverse wave. Sound wave is longitudinal wave. So instead of using Y, you can use something else. X is still X. Suppose I consider this point as X equal to 0. And this is X equal to X. Then if we consider a particle here, it will go in this manner. It will perform SHM in this manner. Likewise, if you consider a point here, it will perform SHM in this manner. When we use Y, we imply this type of thing. Okay? So what we can do is that we can use S. S naught will be the amplitude. So suppose this is a mean position, then this will be S naught back, again S naught back, S naught back, S naught back. Like this, SHM would be performed by the particles of the medium. Okay, sound is a mechanical wave. It requires medium to travel. Okay, and particles of the medium oscillate along the line of progression, along the direction of progression, along that line. Right? So rest is the same. I mean, when we say Y equal to Y naught sine omega t minus kx, then you can use S equal to X, S naught, S equal to S naught sine omega t minus kx. Rest is the same. In case of sound, though, there is another aspect which is very important, and that is the human perception, our perception. And actually, human perception depends on the pressure change. You see, when particles are going to the right side, you have to imagine many particles. It is not just one line. Many particles you will have to consider. Suppose many particles are compressed to the right side, and then several particles are moving away from the mean position. There are regions of increased pressure and decreased pressure that are created. So when the sound wave travels, we have pressure variation taking place. So yes, there is position variation, S equal to S naught, given by that equation. S equal to S naught sine omega t minus kx. Attached with that is pressure variation. If particles go away, if particles come close together, if particles come close together, pressure increases. If particles go away from a region, in that region, pressure decreases. So you have 1 atmospheric pressure otherwise, but when the sound wave travels, that 1 atm can increase little bit, very little bit, and decrease very little bit. So this pressure variation is what our ears read. Okay? So for us, this becomes very important. P equal to P naught sine omega t minus kx. This is a pressure variation. So this is something which is important in the context of sound waves. So you can write the equation in both ways, in this way also and in this way also. Consider this situation. We have one source here, another sound source here. They are identical. They are producing exactly the same sound. Okay? The listener is symmetrically located. Same distance from here, same distance from here. They are in the same line. Fine? Now, as I discussed here, there are regions when particles come close, they go far away. So when particles come close, we call it compression region. When particles go away, we call it rarefaction. So think of compression and rarefaction regions that are traveling due to this S, and also compression and rarefaction regions that are coming due to this, and they are going to the left, here they are going to the right. If we consider these to be identical, how can we consider them to be identical? Maybe both are connected to the same maybe DVD player. Okay, these two could be the loudspeakers and they could be driven by the same CD player. So they can produce exactly the same sound, this and that. So when compression is sent by this, at this place, then compression will be sent by this also at this place. Or when rarefaction comes here due to this, rarefaction also comes here due to this. So the two are coming in phase. Compression, if that comes, compression also comes. Rarefaction comes, rarefaction comes. Or think in this manner, there's a particle here and this source is pushing it to the right. And there's a same particle here and this source will push it to the left. So what will be the net displacement of that particle? Obviously zero, because these are identical waves. Okay, when this wave tries to push that particle to the right, this wave coming from here tries to push that particle to the left. Right? So this particle should be having no displacement at all. But if you place your ear here, and you can very well picturize this, it will sound quite loud because both are sending waves simultaneously. It will sound pretty loud here. Earlier I was telling you that human ears respond to pressure. Even though displacement is zero, human ear perceives it as great sound. That's because of high pressure. Imagine two compressions reaching, or two high pressure things reaching, or two negative pressure, means lower side pressure, but in sync, in synchronism, they reach. Like if atmospheric pressure is P, then it can be P plus something or P minus something. So P plus something and P plus something both reaching. P minus something both reaching. So it means it will be extreme case. P plus something and P plus something both reaching, it will become even more. Or P minus something reaching, it will become even less. It will be P minus more less. Likewise, it will be P plus more. That means it will be enormous sound here. And this is what we perceive also. We do not perceive it to be zero sound. Our ear does not perceive it to be zero sound, even though displacement is zero. Our ear perceives it as great sound. So that's what I meant by this, that in case of sound, pressure way of writing is very important because our ears respond to pressure. And when I say pressure, I'm referring to pressure change. Okay? Now in this context, it is also important to keep in mind that while pattern-wise both are similar, I mean sin omega t minus kx, sin omega t minus kx, there will be phase difference. There will be phase difference if you are representing the same way by displacement and the same way by pressure, then there will be phase difference. You can see it here. When S is 0, pressure is maximum. When one thing is 0, other thing is maximum, then obviously there has to be a gap of 90-degree phase difference. Okay, so 90-degree phase difference is there in these two. You can call this as displacement wave and this as pressure wave. And the same wave can be represented in either of the two formats or both formats. If you are representing the same wave by both formats, you will have to keep a phase difference of 90 degrees. Now, earlier I mentioned about 90-degree phase difference. If it sounded you intuitive, then there is a proof for it. Why the phase difference should be 90 degree when we talk of displacement wave and pressure wave. And by the way, these are not different waves, it's just a way of saying it. Same wave we are talking about. So let's consider a longitudinal wave. Which is going in x direction. Consider position x at some time t. Position x at some time t. Let's say the particle here has displacement s in x direction. Then for this we can write s equal to s naught sine omega t minus kx. Now consider x plus delta x, which means this is delta x. Consider this volume, which is A, because A is the area of cross section, into delta x. Consider this volume A delta x. if density is rho, it is some fluid basically. It could be gas, for example. If density is rho, volume of this is A delta x, then you know density is mass upon volume. So mass of this will be density multiplied by A delta x. A delta x is the volume, so mass will be A delta x into rho of this. Now we are considering some progressive wave which is traveling to the right side. And when the wave travels, it disturbs the particles. So let us say that when the wave travels, then this is displaced by S, and this is displaced by S plus delta S. Okay, this is displaced by S, and this is displaced by S plus delta S. So effectively speaking, delta S shift has taken place to the right side when the wave propagates. In this volume, originally it was this volume, now it is this volume when the wave travels. So initial volume A delta x. Now when this travels by S, this travels by S plus delta S, then the change in volume will be A delta S. And in this figure, it is an increase in volume that has taken place. This is an increase, A delta S. Now, S is this, so differentiate by X, delta S by delta X. Keeping time constant, differentiate. Keeping time constant, it's like partial differentiation where t is constant. So you will get this. So in place of delta S, you can put minus ks naught, this whole thing here. So delta V is this. Now A into delta X, that was the initial volume. This was the initial volume. So writing V, then K I have copied, S naught I have copied, cos I have copied. So this is pretty obvious. Now, we have this formula from elasticity. Pressure is negative bulk modulus of elasticity, delta V by V. In fact, I should say pressure change. Here when I say pressure, I mean pressure change. I want delta V by V. So delta V by V will be minus P by B. So in place of this, putting minus P by B, copying this. So P equal to BKS naught cos omega t minus kx. Obviously, this is the maximum pressure you can have. So in place of this, you can put P naught. Rest you can copy. So now you can clearly see that 90-degree thing is coming, right? Sine and cos. So when we represent the same wave by displacement equation and by pressure equation, then there is a 90-degree angle difference or phase difference. And of course, P naught is BK S naught. That can be a useful formula. P naught equal to BK S naught. Yes, any questions or we proceed further? Consider in some fluid, sound wave is traveling to the right side, which is positive x direction. And this is the equation which we have covered already. At x position, let's say pressure is P. At x plus delta x position, let's say pressure is P plus delta P. Then force here will be, force is pressure into area, PA, and force here will be pressure into area, P plus delta P into A. So this force to the right, this force to the left. That means on this system, whose volume is A into delta X, on these particle system, the net force is to the left and it is P plus delta P into A whole multiplied by A minus PA. So it is A delta P in magnitude, and because I am taking right direction as positive, this force is to the left, it is minus A delta P. Okay, so this force was to the right, this was to the left, so this is to the left. If this is S, then the pressure wave will be this. Delta P by delta X keeping time constant will be this. It's like partial differentiation. In place of delta P, put delta F by A minus, and you will get this. In place of delta P here, put delta F by A minus, and you will get this. We are talking about this system of particles. Force will be mass into acceleration. Mass is density into volume. So density into volume A delta x into acceleration A will be this. Small a is the acceleration. Simplify and you will get acceleration equal to this. Now this is one way of getting acceleration of particle. Other way is you find this derivative 2 times. Partial derivative with respect to time, 2 times you find it out. So you consider this equation, differentiate once partial, differentiate once more partial, and you will get the same acceleration. You must write each step in your notebook. So acceleration obtained by this method and acceleration obtained by that method, equate the two. Equate the two. Cancel as much as you can and you should get this. What are we trying to do? We are trying to find out the formula for speed of sound. We had this discussion for for wave on a string. So there we had a derivation also, here also we are deriving. But we know that k is 2 pi by lambda or omega by v, same thing. 2 pi by lambda is same as omega by v. So in place of k, put this and omega square will get cancelled and you will get v square equal to d by rho. Now that means v is under root of b by rho. B is the bulk modulus of elasticity. Rho is the density of the medium. What is the formula for speed in case of a string, traveling wave on a string? What is the formula for speed there? I don't hear you.
So under root of tension upon mass per unit length.
Under root of tension upon mass per unit length. So there also you had 2 things, elastic behavior and inertial behavior. And here also you have the 2 things, the elastic behavior and the inertial behavior. So whether it's a case of speed of sound or it's a case of speed of progressive wave on a string, the speed depends on the 2 properties, the elasticity of the medium and the inertia of the medium. Okay?